In the grinding of ceramic materials, it's the same interactions have to take place, but only difference is the grain work interaction can be cutting, will lead to brittle fracture or ductile deformation. There is hardly any plowing, or there will be a lot of sliding. And this is from the literature. The whole thing you can get it from the reference for this. Essentially what they say is, when the radius of the indentor is large and the applied force is large, it doesn't matter what you do, you'll always have cracks in ceramics. When the radius of the indentor is small, even then when the applied force is large, you'll have brittle cracks in a different kind compared to, you will also have a median crack in addition to lateral cracks. Whereas if a ductile material, whatever the radius you use, whatever the force you use, will always be deformation. But there is a sweet spot in ceramic materials where the radius of the indentor is small, the force applied is small, you end up with having ductile deformation. Now, the reasons for the will vary from the material, its fracture toughness, so on and so forth. But essentially, you're trying to operate in this regime. And if you operate only in this regime, it will be called ductile regime grinding. But on the other hand, you can always be sure, because of this interaction, there will be some interactions taking place in this direction towards brittle fracture, some taking place towards ductile deformation. But it depends upon the chip thickness, which is the volume of indentation. It depends on the force per grain. It depends upon the abrasive particle size, which influences both of them. So essentially, the more you skirt towards the left-hand side, you have ductile deformation. The more you move to the right-hand side, you've got brittle fracture. So in addition to general issues of grinding that you normally deal with, you have to manage this balance. Essentially, that's what makes the difference between ceramic grinding versus grinding of ductile materials. Okay, now we have understood the science, but you have to translate that into application. That's what engineering is all about. So that same picture I showed you now becomes translated into how is it affected as per machine tool properties, processing tool properties, work material properties, operational parameters during the process and output. It'll take me some time, so I would not go into the details, but you can go to another time. So essentially, you're trying to stay mostly on the left-hand side and never go into the right-hand side. But because you can live with some degree of brittle fracture, as long as it's not substantial. And you can live with some brittle fracture and roughing, but you can get rid of in the finished grinding, just like you will remove the surface roughness, which will be very coarse and rough grinding in ductile materials, and reduce that in finished grinding. Except here, you're not trying to manage the surface finish, you're trying to manage the micro cracks. And essentially, but typically, most of the literature had said ductile regime grinding operating only in this regime, but that is not economical and practically feasible. So what we took was, we took the what is available in the literature, we came up with this model, we understood that we had to stay in a certain regime. Within that regime, you can design a roughing grinding cycle and a finished grinding cycle for economics and productivity and so forth. And you could indeed achieve very high surface quality and low brittle fracture and cracks. Now, so all the other principles of tribology apply. So you have to be a very good tribologist as much as a machine technologist if you want to be a good grinding person. So in fact, I would argue that grinding is machining plus tribology. Then machining is a subset of grinding, as opposed to people thinking of grinding as a subset of machining. As a scientist, I'm not here to make politics or arguments or anything like that. But that is what science allows you to think differently from others. Now, you can create, okay, once you're, then you go crazy, because scientists is also supposed to demonstrate his capabilities in areas that did not exist before. Here is A1 and A2 are two surfaces, both on the same material, except when thermal issues are not managed, it's not brittle fracture. When thermal issues are not managed, you'll end up with A1. When thermal issues are managed, you get very good surface in A2. Also, you can grind very mirror-like surfaces in a cylindrical surface or a flat surface. You can take a hollow tube and grind it into a worm and create a spring out of it, and then collapse it like a metal spring. If a metal spring, you bounce it, you can bounce it forever, it may not break. Ceramic spring also, by the way, I have bounced it with great degree of confidence. Except you bounce it 10 or 20 times, it will break eventually. But you can make ceramic springs and collapse them just like metal spring. You can grind ceramics to very thin diameter as shown in E without any end support. And you can, because the force per grain, the kinetic conditions are so good that you can manage that. And because material has its own inherent strength. You can grind a silicon wafer, which is like a brittle material, and bend it into a plastic sheet of steel. You can grind a sapphire so plain and so good in surface quality that it becomes transparent. Now,